Start the recording here. Here's contact information. My office is in room Chem 120, which is down the hall over here. Email. This email has limited space, so sometimes I use an alternate email. If the email box gets too full, it blocks me from sending out emails. So you can try this one. Archibald.elcamino@gmail.com. Phone number, you can leave me a voicemail. I'm at extension 3240. My office hours, I haven't finalized those yet. But this is what I'm thinking. The office, if you stick around after class, I can answer most of the questions if you have any at that time. But for the formal office hours, we'll probably have those after lab. So at the end of the lab, just stick around and go through those. I'm also thinking about having a Zoom session for office. And that would be, I was thinking at night, but some people said they can't make it at night. So I'll have to think about it some more. We'll just schedule those as needed. But maybe I'll just have one. What time is good usually? Night, late night, evening, afternoon? So after 9? Yeah. All right. Well, I'll try to think of something then. Oh, okay. Monday, Wednesdays. Maybe I'll have one late, after 9. Monday, Wednesday, and then maybe one at another time. I'll see. Maybe pass out a survey or something. Figure it out from there. So pretty soon I'll have the office hours, but just stick around after class if you have any questions right now. Here's a catalog course description. There are a lot of topics we're covering. Elements and compounds of periodic groupings, transition metal complexes, chemical equilibrium, chemical thermodynamics, kinetics, atomic and molecular structure, aqueous solutions, and ionic equations, oxidation reduction reactions or equations, electrochemistry, and nuclear chemistry. But basically, there are a few main topics like equilibrium. Chemical equilibrium, we're going to do like 4 chapters worth of that. And so that's a big one. Thermodynamics and kinetics, another way to go on. Redox, another big one. So a lot of different topics, but I think fewer than in Chem 1A. Chem 1A hits so many different things. Chem 1B is more of maybe 3 themes to it. The course objective, you read through that. We also have SLOs, student learning outcomes. This first one is being able to predict chemical reactions. If you're given 2 different compounds or an element in a compound, what do you expect might form from that? And can you write the equations for that and predict the driving force, that type of stuff? The other one that might give us trouble this semester is goggles. With these face masks. I don't know if you guys have used goggles with these face masks. Have you? Was it okay? No. Yeah. They tend to fog up. We have leftover goggles. Every semester there are students who just leave their goggles in their drawer, or they don't want them anymore, they don't need them anymore, so they just leave them. So if you want, if you don't have a pair of goggles, you're welcome to take any of these. Here. You guys want? Well, there's some garbage in here, but yeah, you can come up during class or something. We'll have a break. We'll have plenty of breaks. You can take a look at it. Somebody used this as a garbage box too. But we have other goggles. Some of them are in better shape. I don't know, in the stock room. So this is the other student learning outcome. Just put on safety goggles. So it's pretty simple. Let's take a look at the required materials here. So Petrucci, you're going to have the homework for that, but there are other textbooks as well. It's just that Petrucci is on the harder end of the spectrum. So Petrucci would be considered like an honors level textbook versus some of the other general chemistry books out there, which are a little easier. Problems aren't as challenging. So Petrucci is a challenging book, and so this is why they've been using it here to keep the level at that honors level. Number 2, catalyst. This I didn't realize went out of print. I thought it was still available because Pearson is still in business, so just assumed we could get it. But I think I was talking to the bookstore right before classes started, and he had mentioned it isn't very profitable for them to do these custom published lab books, so that's probably why it went out of print. Because this is the same company that does Petrucci here. Well, Petrucci, being that honors level, the textbook isn't as popular, which is good because that means the 11th edition has been going on for many years. The more popular books, they revise it like every 3 years, which means you have to buy a new book every 3 years. And so this book's been around, so you can find copies of this online pretty easily too. The ebook is nice because the ebook links to homework. And, it's pretty useful. And so forget number 2, just strike that. But what I'm going to do is I'm just going to post the labs on Canvas. And so you could just go to Canvas and download them from there. Number 4, though, you'll need that. This is the composition notebook. This is going to serve as your lab notebook here. This is a regular standard comp notebook, except with graph paper. So here's one from a while back. This is Chem 1B here. It has to be with a sewn binding like this. It has to have a permanent binding. And so you can't just buy like a notebook of graph paper, the ones that you can tear out and use, or the spiral bound notebooks. Those aren't considered laboratory notebooks. Something with a permanent binding where you can't tear out the pages, or you're not supposed to tear out the pages. This is what we'll use here. Some people get 2 of them, one for homework, one for lab. For lab, you definitely need a sewn binding here, but for homework, you don't. If you want to buy a spiral bound notebook, that's fine, or whatever you want to do for the homework. I'm going to be collecting homework this semester. So what you can do is you can just have a notebook dedicated to, Chem 1B homework, and then you could turn in the notebook. You don't have to tear out the pages. I'll just check off the homework and just give it back to you the same day. So that way you don't have your homework all at different places, let's say, different locations. The safety goggles, if you want to buy a new pair, they sell these at the bookstore. These are called visor goggles. So everybody has the same. These goggles here aren't really approved for chemistry. These are safety goggles. Safety goggles have impact resistant. Actually, boy, these don't even seem impact resistant. Yeah, these, I don't know where these came from, but these are not very good at all. But they're supposed to offer splash protection, and then these side vents. If they were capped, they would be acceptable, but these aren't. So I think I'm going to have to toss these ones away. All right, so safety glasses aren't approved either. They have to be goggles. Safety glasses leave a gap, between your cheeks and your eyes, the lens, and splashes can get up in there. So, okay. Scientific calculator. Most of you already have a scientific calculator, but you might consider getting an additional calculator, one that has an equation solver built in. So let me show you what I have. They changed the design of this. I'm not sure. It's the same. Probably it. I have this, the Casio FX115 ES Plus. And it's like, it's not the cheapest. It's the next level up from the cheapest. Last time I bought it, it was $18. I bought it at Target. This is $20 at Office Depot. That's not bad. This is the latest version here. Mine looks like this. It's 991EX. Maybe just, yeah, basically this looks like my calculator, but this is a $30 calculator. So I'll have to take a look again and look at it in detail. But something like this would be good. Yeah. And the reason you want a calculator like this is this calculator can do quadratic equations. And so you just plug in A, B, C, and it will give you X1 and X2. We're going to have we're going to be solving a lot of quadratic equations this semester. And those are, not that difficult, but time consuming to solve. And so it's much better if you can just solve those quickly, especially during exams, and these are fine for that. It doesn't have to be a Casio, whatever you have that has an equation solver built in that's non-programmable is acceptable. If you don't want to buy another calculator, we have basic scientific calculators from the stockroom that you can check out and borrow, but those don't have the equation solver. And, you'll have to solve the quadratics by hand. We try to avoid solving the quadratic. We try to come up with some tricks, so that we don't have to go through all that work. But sometimes those tricks don't work, and we'll have to eventually solve it by hand. Okay, the other item will be these fine point permanent markers, just Sharpie pens. We have some for the lab, but it's nice to have your own. That way, if you need to label, there are two ways you can label, three ways we can label things. The first is by pencil on this white pad. So if you write with a pencil, you can erase it if you need to. The second way is we can just write directly on the glassware. So if I want to write number 1, I can do that. If I want to remove it, I can just rub it off. Or if need be, use some alcohol to take it off. The third way is we have this green tape here. This green tape people use for labeling glassware here. And so it's easy and it doesn't leave a residue when you peel it off. So 3 ways. But it's nice to have a Sharpie around. That should be in the recommended. This is not really mandatory. A lab coat is not mandatory either. I have a lab coat. A lab coat is really nice to have because it'll save you a lot of money in clothes. What happens is, you end up leaning against the counter and nobody had cleaned it. Maybe there's some acid on there, or maybe there's some like oxidizer, like bleach on there. And then you go home and you notice you have this line going across or holes in your clothing. Lots of my shirts have holes in it because sometimes you'll get a splash. And you don't notice it because tiny droplets hit your clothes until you wash your clothes and you see lots of little tiny holes or bleach spots in your clothing. So a lab coat's nice to have. This lab coat I bought off Amazon, $15. The last lab coat I had, it was required. I had to buy a lab coat at UCLA, and the lab coat had to be cotton, not a synthetic fiber. Had to be cotton because of fire resistance. And that lab coat at the time was $70. Now they're over $100. But it's up to you. You can buy one of the very nice lab coats, or let's see. Or just your basic one, like this, It's still about the same price, $15. The price hasn't skyrocketed, so that's nice. But it's a synthetic fiber. In some labs you can't wear synthetics. Okay, the other thing that's nice to have are, and actually these are required now at UCLA, but they're optional here, are nitrile or latex gloves. When I first started working in the labs, I didn't like the gloves, but latex, because latex is hard to work. They don't breathe very well, and your hands can get sweaty. And so nitrile is much better. Not only in terms of breathing, but also in terms of chemical resistance. Not all gloves are like impermeable to chemicals. Eventually, what happens is the chemicals will saturate the plastic, and once the gloves become saturated with that chemical, then the chemical can diffuse rapidly through the glove. And so it depends on what chemicals you come into contact with. That dictates the lifetime of the glove. So some gloves will last like 10 minutes because the chemicals go right through it. Other gloves will last all day or and then some. And so, anyway, that's why disposable. None of these gloves are meant to be long-term use. But nitrile will last a heck of a lot longer than latex. So, I recommend those. All right, if you have any questions, let me know. Required assignments, you're required to, complete the lecture and lab, or come to lecture and lab meetings, especially the lab meetings. You don't want to miss too many labs. So the lectures I'm going to try to record here, but the labs are set up. So if you do miss a lab, you might be able to make it up,
Like, for example, let's say you miss the afternoon lab. You can come to the morning session and try to make it up there. That's possible. Or you could try to make it up, at another time. But for some of these labs, there's specialized equipment that they have to put out. And so if the stockroom puts it out for just that week, and then, the following week they remove all the equipment, they don't want to set it up again. And so those labs you can't make up. So, make every effort that you can to come to lab. If you do miss a lab, then we'll try to see if it's possible to make it up. For exams, that will be done on a case-by-case basis, depending on the circumstances. So try not to miss the exams as well. Lectures, well, you probably can make that up using the videos. Hopefully, I don't forget to record the videos. All right, so the way the points are being broken down, we're going to have 9 exams. The exams are going to just cover one chapter, except for the first exam. The first exam is going to cover this chemical properties plus part of chapter 24. Okay, the second exam is going to be chapter 15. So after we finish chapter 15, then, a week or a few days after that, we'll have the test on chapter 15. We'll have 14 quizzes, so that works out to about a quiz once a week. We have 16 weeks. We'll have paper homework. Those 10 homework assignments worth 10 points each. The labs, the standard labs are worth 12 points, except we're going to have some worth 30 points. This qualitative lab is going to be worth 30 points because it's a very long lab. You spend a lot of time doing it. But the synthesis lab, the titration lab, and the rate law lab, these are just standard experiments, but what we're going to do is we're going to do a formal lab write-up for those, like a standard laboratory report. Standard laboratory report is not too bad, it's just you have to write things in a certain format, and so this is good to get familiar with that particular format that laboratory reports are written in. And so we're going to do those for these 3. And then we'll have a 200-point comprehensive final. This is all going to add up to about 1,000 points. Yeah. Just shy of 1,000 points. Okay, your grade, here's the cutoffs. It's going to just be based on the percentage of the total points. Now, like at UCLA, they keep the lab and the lecture separate. So you could fail lab there and pass lecture. Here, lab and lecture are together. So if you fail lab, technically you could still pass the class because most of the points are in the lecture part of the class, not the lab part of the class. But since UCLA doesn't want students to pass chemistry without passing lab, then they require us to fail you. If you fail lab, you fail the class. Are you guys familiar with that policy? Too much? Yeah, okay, good. A note on cheating here. Special needs, if you have any special requirements, let me or the Special Resources Center know. Changes, I'll post the changes, maybe, I'll announce them in class, but maybe I'll post those on Canvas or wherever else. And then we have the definition of chemistry. The definition of chemistry here, I like this definition here, or 1 or 2. The science of the composition, structure, properties, and reactions of matter, especially of atomic and molecular systems. That's pretty good. The only thing I changed about this definition is when I think of properties, I think of physical properties and chemical properties. And so I would put reactions in properties, because properties, one of the properties of a substance are the reactions that substance undergoes. And so when we study chemistry, we always are interested in the properties. And to better understand the properties of matter, we need to know what it's made out of, the composition. And not just only the composition, we need to know how it's structured. and then we can correlate those with properties. And so this is what chemists will spend a lot of time researching: the composition, structure, and properties of matter. All right, let's take a look at the schedule here. So this is week one. In week one, today we're doing a continuation of chemical properties we started yesterday. And then we'll start chapter 24. We're just going to do the first 3 sections of chapter 24 and then jump to chapter 15. So we're going to be jumping around in the book. From 15, which deals with equilibrium, we'll go to 16, which also deals with equilibrium, but acid-base equilibrium specifically. Then we go on to chapter 17. Chapter 17 also deals with equilibrium, but acid-base equilibrium part 2. And then we go on to chapter 18. Chapter 18 also deals with equilibrium, except this will be solubility product, which is like salts, insoluble salts, and complex ion equilibria. Complex ions deals with complexes. These are special ions and special compounds, which we're going to talk about in chapter 24 right at the beginning. We're going to be looking at complexes, how to name them, and their structure. Okay, then after chapter 18, we're going to drop back down to chapter 13. Chapter 13 is going to talk about thermodynamics. This will be thermodynamics part 2. You already did thermodynamics part 1 in Chem 1A. And so chapter 13, then we'll have spring break in week 9. Week 10, we'll have thermo. Week 11, we're going to start kinetics. Week 12, we're going to jump, we're going to jump from 13 to 20, which is kinetics. So continue that here. And then from chapter 20, we're going to drop down to chapter 19, which deals with electrochemistry. Kinetics deals with speed of reaction, electrochemistry deals with like redox chemistry, batteries, that kind of stuff. Then from chapter 19, we're going to go up to chapter 24, finish that chapter, which is transition metal complexes, and then on to chapter 25. We're going to end with chapter 25. Chapter 25 deals with nuclear chemistry, and we'll do that in weeks 15 and 16. Actually, it depends if you count spring break or not. 16 and 17 if you count spring break. And then we'll have the final exam. One thing here, if you look, on Tuesdays and Thursdays, we'll have lab days. So let's take a look at the labs next. Actually, we don't have any labs scheduled. The first time we're actually going to do something related to lab will be Thursday next week. Here we're going to have a lab intro, safety, and check-in. We aren't actually going to do any labs until March 1st, the 3rd week. Here we'll do Le Chatelier's principle. I'll post the procedure here on Canvas, and then you can just download that. Then on March 3rd, Thursday, we're going to have hydrolysis of salts at another lab. Also will be posted on Canvas. Then 4th week, we're going to have synthesis of a transition metal complex. And then continue. Yeah, so this will be a 2-day lab. Then pH titration, which will also be a 2-day lab. And then we're going to go into the computer lab and do some work. So the computer lab's down the hall in Chem 108. Then we start qualitative analysis. Qualitative analysis is a big part of the lab. So we'll have day 1, day 2, day 3, day 4. Day 5. And the final day would be day 6. So 6 lab periods of qualitative analysis. It's a lot. We're back in the computer lab, Chem 108. Then kinetics lab, the rate law determination, day 1, day 2. Back in the computer lab. Remind me I need to reserve the computer lab. If somebody beat me to it, then I'll have to change my schedule around a little bit. We'll see. Hopefully nobody's reserved it yet. Molecular models. And should have electrochem. Yeah, electrochem. And that's pretty much it. One thing you need to note is this. You know, on June 7th, last week, Tuesday, we'll have cleanup and checkout. Let's say something happens and you need to drop the course. If you have to drop the course, don't forget to check out. You can check out before the last week, you know. Otherwise, what they're going to do is they're going to place a hold on your transcript. The only way to release the hold is to pay a fine or something or whatever they have for not checking out. It's not much. It's like $5, but, or was. I don't know if they changed the price. But still, that's easy to do, checking out. All right. All right, any questions about the schedule? Uh-huh.
So this, a couple days after we're done with chapter 15, we'll have our first exam.
Right. Yeah, that's a good question. The thing is, none of the exam dates are written in there. And there's the reason for that. The reason for that is if I fall behind schedule. If I fall behind schedule and I have the exam date written there, because what I want to do is I want to test for the entire exam. So let's say, you know, usually at the beginning I stay on schedule. So let's say I do stay on schedule and I'm done with chapter 15 here. Then normally what I'll do is on the following week, we'll have the test. And so the test is going to be here. Now, I like to have the tests on lab days because lab days are longer than lecture days, but that might change. If I do have the test on the lab day, what that's going to do is it's going to shorten the lab period. And so what I might do is I might, you know, chop off some of the experiment. Maybe we'll skip this section or not do that part of the lab. This lab is a very quick lab. It doesn't take much time. So if we have the exam on this day, we can have both. We'll have the lab and then the test. Usually we'll do the lab first and then the test after. And then once you're done with the test, then you can leave. You don't have to stick around and wait for the lab to begin if you finish early. And so that's the way it's going to work. So let's say chapter 16, we finish here or here. Then, you know, a few days later or up to a week later, we'll have the test, chapter 16. That works great until we get to the end of the semester. When you get to the end of the semester, then things get compressed. So this is what I do. Like, I'm not going to make you come in over the summer to take the test on chapter 25, right here. And so normally what I do is for like chapter 25 nuclear chemistry, I'll incorporate some questions into the final. And so it won't be a full test. You know, if you look at the number of chapters, we have more than 9 chapters that we're covering, but we're only going to have 9 tests. That's because chapter 25 and maybe chapter 24, the last part of chapter 24, will be on the final exam rather than a separate exam. Chapter 25 is just a brief survey of nuclear chemistry. We aren't going to go in as much depth as we go in on the other chapters. You know, nuclear chem, it's a pretty interesting topic, but we it usually gets shortchanged in this. You know, being at the end, we might end up just doing 1 day of nuclear chem or 2 days of nuclear chem. But if I can stay on schedule, then we'll have a lot of nuclear chem. Okay, any other questions? Okay. All right, we're going to talk about the where did I leave off last time? We were talking about chemical properties, were we? And then I told you how many different types of chemical properties are there? 3. And I find this classification, you know, different people have different classification schemes. You know, you ask different people, how many different types of chemical reactions are there in nature, you know, in the universe? And in the universe is quite diverse, but let's just say, you know, on Earth here, how many different kinds of chemical reactions are there? And some people will say, yeah, it's got to be some huge number, you know, tens of thousands, hundreds of thousands of different kinds of chemical reactions, right? But if you look at those, you know, let's say we take 100,000 chemical reactions, then we'll see common features to those. And, you know, we can group those depending on what the common feature is. And so what is the common feature for me? When I think of chemical reactions, I look at what drives the reaction. You know, why does that reaction occur? What's driving the reaction forward? And that I call the driving force for the reaction. And so when I look at chemical reactions, I see 3 types of driving forces for chemical reactions. So what we're going to have is 3 types of reactions depending on the driving force. So you could have something like, say, a combination reaction, which is an acid-base combination reaction, and a combination reaction, which is a redox reaction. And you might say both of those are combination reactions, but both of those don't share the same driving force. The driving force for the combination acid-base reaction is totally different than the combination redox reaction's driving force. And so I don't like to classify both of those into the same category because we look at them differently. We think about them differently because what's driving those reactions is different. And so these are the 3 the 3 major categories of reactions that I like to break things down into. And how did I talk much about it, or did I just say what they were?
You kind of just said what they were.
Okay. I think we ran out of time at that point. So let's take a. Did I tell you the 3 types of acid-base reactions?
Yes.
Okay, Arrhenius, Bronsted, Lewis. And can you give me some examples of redox reactions?
Combustion,
Yeah, combustion,
single replacement.
single replacement. That's good. And then metathesis. Yeah, double. Okay, good. All right, let's take a short break. Let's take a 10-minute break, and then we'll start again from there. We'll just jump into reactions. So nitrogen, we'll throw in the center. It's less electronegative than the oxygen. Okay, then what we'll do is we'll just go ahead and bond the oxygens to the nitrogen like that. And we try to avoid oxygen-oxygen bonds. Oxygen-oxygen bonds are what we call peroxide links. Peroxide links are fairly unstable, and so I wouldn't have a chain. Having a chain of carbon atoms is no big deal. Having a chain of oxygens is really pretty unstable. Now, where do we put the hydrogen? Should we bond it to the nitrogen in the middle or the oxygen?
Oxygen.
The oxygen. one of the rules is we recognize this as an acid. You know, element H starts off first. And so if it's an acid, then the acid hydrogen always goes on the most electronegative. And so we just pick one of these. Just pick this N1 here. And put that there. Okay, let's see. We've used up 2, 4, 6, 8 electrons. How many electrons do we have? So hydrogen has how many valence electrons? 1. Nitrogen? 5. And then we have 3 oxygens. Each oxygen is 6. So that gives us 18 electrons. 18, 19, 24 electrons. So we have extra electrons here. The extra electrons, usually we try to complete the octets to the terminal atoms, or the more electronegative atoms first. More electronegative atoms would be like the oxygens here. So let's go ahead and complete the octets to the oxygens first. We'll do these. This is called a terminal oxygen. This is called a bridging oxygen. So I'll complete the terminal oxygens first and then do the bridging oxygen, like that. Bridging, it just bridges between 2 atoms. Yeah. So how many electrons have I used up? Well, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So I've used up all 24 electrons. So does that look like a good structure to you? Or does something look off about this structure?
Shouldn't it include the nitrogen?
I'm sorry?
Shouldn't the nitrogen be complete?
Yeah, what's wrong with the nitrogen?
It only has 6.
It only has 6. It doesn't have an octet, 2, 4, 6. So that's less than an octet, but I've ran out of electrons, so what do I need to do? I can't add another pair. I'd like to add a pair of electrons here on the nitrogen, but that would make 26 electrons. I don't have 26 electrons. So I can't add a pair of electrons on the nitrogen.
It would share with one of the oxygen.
Yeah, it's got to share with one of the oxygens. So let me just pick this oxygen here, this bridging oxygen, and I'm going to take one of the lone pairs here and make it a bonding pair. And so we have a double bond like that. How does that look? Now, it looks good for nitrogen because nitrogen now has a octet. Okay? So nitrogen has this octet. Does it look good? Actually, it doesn't look so good. What's wrong with it? It's not the octet. The octet rule is fine. There's something else wrong with it. What's that something else that's wrong with it? The shape is way off, but you know, Lewis structures, you don't have to worry about shape unless you're asked. You know, it's not T-shaped like that. The charges, what kind of charge? The formal charges. The formal charges are not good. So do you guys remember formal charge? How to calculate formal charge? Do formal charges? It turns out when we try to analyze the composition and the structure, we try to look at how the electrons are distributed in here. And there are different ways of counting electrons. There are like 4 ways of counting electrons that we consider. Well, the octet, well, right, octet is number 4, but formal charge, we look at formal charge. Formal charge, the way we count the electrons, actually, maybe I'll still put in the octet in here. Let me do the octet as 1. We'll call formal charge 2. So when we do the octet, we look at total number of electrons surrounding the atom directly. So nitrogen is good now, 2, 4, 6, 8. These other electrons on oxygen belong to the oxygen. But we double count. So when I look at this oxygen here, it's 2, 4, 6, 8. So I count these twice. Once for nitrogen, once for oxygen. But these lone pairs belong entirely to that oxygen. That's oxygen. Formal charge, we don't double count the electrons. In formal charge, we divide up the electrons. And the rules for dividing up the electrons are pretty simple. It's just one rule. Formal charge, we make an assumption. We assume 100% covalent bonds. So, in other words, it's 0% ionic, 100% covalent, which means what? Covalent means the electrons are shared. And so 100% covalent means they're shared evenly. So if I have 2 electrons, then one atom gets one, the other atom gets the other. And so when we do this here, I like to divide up the bonds. So here I have a bond. This bond consists of 2 electrons. It's 100% covalent, so oxygen gets 1 electron, nitrogen gets the other. And then we divide up the electrons and then count. How many electrons does oxygen end up with? 7. How many electrons did oxygen contribute?
8.
How many electrons did oxygen contribute to the structure? 6. It put in 6 electrons into the pool of electrons, and once the structure was built, how many electrons did it end up with? 7. So it came out ahead 1 electron, right? It only put in 6 electrons, it gets 7 electrons back. That's pretty good. And so that means this oxygen ends up with an extra electron. An extra electron is negative charge, so we get a formal charge of -1. This oxygen down here is the same. This oxygen gets a formal charge of -1. Now, formal charges I like to circle, and I don't write the 1, I just write negative. Negative just means 1. If it's -2, I'd write -2. But -1, I just write negative, circle it. How about this oxygen here? What's the formal charge on this oxygen, the bridging oxygen? Yeah, +1. If we divide up the electrons here, I have a double bond. So double bond has a total of 4 electrons. 2 to nitrogen, the other 2 is oxygen. Then I have a single bond here. And so when I count up the electrons, I end up with 2, 4, 5. This oxygen contributed how many electrons to the structure? 6, but it only got back 5. You know, this is what some people in California complain about. You know, the taxes. You know, the taxes for federal taxes. They send, let's say, for every $100 they send to Washington D.C., how much of that money makes it back to California? Apparently, a lot less than $100. So this is like this oxygen here. This oxygen contributed 6 electrons to the pool, and it only got back 5. So it ends up at a deficit of how many electrons? It ends up at a deficit of 1 electron, which gives it a +1 charge. How about this nitrogen here? It only has 4, but it contributed 5. That means positive, right? So this nitrogen will have a positive formal charge. And this hydrogen will be 0. Normally, if it's 0, we don't write it, you know. We just write the non-zero formal charges. And so these are the formal charges. So you look at this, one thing to note is that all the formal charges add up to the net charge. So minus, plus, plus, minus gives us 0 net charge. HNO3 has 0 net charge. It's a neutral molecule. This formal charge arrangement is not necessarily bad. It's just, if we have something better, that would be preferred. Is there something better than this particular structure? And the answer is yes. Yeah, if we just change the position of the double bond. So if we compare this structure, and rather than making the double bond to the bridging oxygen, let's leave the bridging oxygen alone and make the double bond to a terminal oxygen, like the top one here. It doesn't matter which one you pick. And we end up with a structure like this. Okay, so what are the formal charges here now? Like if we look at this top oxygen, can you just look at that and tell me what the formal charge is? That's correct. The formal charge of this top oxygen is 0. Here, the way we count it is 1, 2, 3, 4 belongs solely to this, and half of these belong to that. So 1, 2, 3, 4, 5, 6. 6 electrons that contributed, 6 electrons broke even. So it's 0. How about this nitrogen here?
It's still positive.
It's still positive. It still ends up short 1. How about this bottom oxygen here?
Still negative.
Still negative. And the bridging oxygen?
0.
0. And this terminal hydrogen?
0.
0. And so when we compare, actually, we don't necessarily write the zeros. Let me get rid of the zeros here. So when we compare these two, we have fewer formal charges. And so more of the atoms, break even, and we have fewer winners and losers. And then in that case, it's more stable. Because, like, for example, let's compare these two oxygens. One oxygen won an extra electron, the other oxygen lost an electron. Does that seem like that's stable?
Mm-hmm.
I mean, they're both the same element. They're both oxygen. So why would one oxygen lose and the other oxygen gain in the same structure? And so this situation isn't as stable, And so you declare this oxygen the winner, this oxygen the loser. Whereas, okay, this oxygen won, but it didn't take an electron from any of the other oxygens. So if you had a tug of war for an electron between two oxygens, which oxygen will win? Well, if it's a tug of war between two oxygens, it should be fairly even, right, or a tie. But here, this is we just end up oxygen versus nitrogen. Yeah, that's okay. But you know what? We probably can get rid of this. You know how I can get rid of this formal charge? Maybe one way to get rid of this is to, let's say, share some of this electron. Oxygen came out ahead with nitrogen. How could it share? We can just make another double bond. So let's try that. Let me write it out this way. This. So let's get rid of that formal charge completely. Here. Now take a look at this. Do you see that? When I look at this, all the formal charges are now 0. So this looks like the optimum structure. Nobody comes out ahead. Nobody comes out the loser. Everybody breaks even. That's fair. And so is that the best structure for this? Yeah, it would be the best structure based on formal charge, but we don't base Lewis structures entirely on formal charge. We base Lewis structures on first the octet rule and then formal charge. And so what's the problem with this structure here? Yeah, this is a violation of the octet rule. If we look at the octet rule, we should have a max of 8. And when we do the count for nitrogen, octet we count differently. We count all of them. 2, 4, 6, 8, 10. That's not an octet. Nitrogen would have a dectet, 10 electrons. So can we violate the octet rule? Sometimes we can violate the octet rule. Rules, there's sometimes exceptions to the rule. So sometimes we can violate it. So for example, phosphorus, sulfur, violate the octet rule frequently. Phosphorus and sulfur containing compounds frequently have something called an expanded octet, like 10 electrons, 12 electrons you could have. But second period, boron, carbon, nitrogen, oxygen, fluorine never violate the octet rule. And so for these ones, we shouldn't call it a rule, we should call it a law. This is the octet law. If you're in the second period, you cannot violate the octet rule. It just doesn't work. This would be too unstable. And so we have to eliminate this structure. Now, however, it is a rule, it isn't a law. Because, in Chem 1A, you've seen lots of different things, like, for example, PCl5. PCl5 would have 5 chlorines bonded to phosphorus, this trigonal bipyramidal structure. So this is a violation of the octet rule, because here, when we look at phosphorus, it has 2, 4, 6, 8, 10. Phosphorus and nitrogen are in the same family, but nitrogen will not violate. And so for nitrogen, it's a law. For phosphorus, it's just a rule. There's exceptions to the rule. That's one of the distinctions between a rule and a law. A rule, you have a lot more exceptions. A law should have a lot fewer, if any, exceptions. However, at the end of chapter 8, I think it was, or chapter 9, or maybe it was chapter 10. It's been a while since I taught it. At the end, they're saying that it's not really an octet rule. Perhaps we should rename it an octet law. They're saying that if you look at the hybridization, what's the hybridization around phosphorus here? There's a trigonal bipyramidal. Would be, what would it be? SP hybridized, SP2 hybridized, SP3 hybridized, SP3D hybridized, SP3D2 hybridized. What do you predict for the hybridization around phosphorus? SP3D hybridized. And so we expect this to be SP3D hybridized orbitals in a trigonal bipyramidal arrangement like this. But quantum mechanical calculations, SP3D should be 20% D character. So these orbitals should have 20% D character from the D orbital contribution to this hybrid orbital. But the quantum mechanical calculations show like 0% D character. If 0% D character, what they're proposing is that there's no violation of the octet rule. The octet rule is always maintained. In fact, it's not a rule, it's a law. The octet law says you do not violate, that is, you do not go over 8 electrons. So what they hypothesize is a combination of bonding. If we cannot violate the octet rule, then what we have to do is we'll do this. We'll put 4 chlorines covalently bonded to this, and that makes the octet. Well, what happens with the 5th chlorine? Or the 6th chlorine if you have something that's like that? Now what happens to the additional? Well, the additional one is, okay, so now we have our octet, right, with 8. I don't know if you covered this in Chem 1A, but this is covered at the end of the chapter. I usually cover this, but depends on, you might have or you might not have. The 5th chlorine is not covalently bonded to it. the fifth chlorine is what we call ionically bonded to it. And so when we look at the formal charge on phosphorus here, it's going to be positive. And so we're going to have a positive charge on the phosphorus because phosphorus gave 5, it only ends up with 4. And then we got this negative charge on the chlorine, which we call chloride. And so we have an ionic bond holding the chloride to the phosphorus. Now they're going to be resonance forms. There are going to be 5 resonance forms, so we can move the chloride into any one of the 5 positions here. So the bonding looks even. So the octet rule is very important. Sometimes we could have expanded octets or apparent expanded octets. So the thinking right now is there's no such thing as an expanded octet. It's a combination of covalent and ionic bonding. You could look at that. That's in the very last section of bonding, Lewis structures, I think, in Chem 1A. But for sure, for second period, it's a law. And for second period, it never violates them. And so even though this one looks great based on formal charges, it's bad based on the octet rule. So we'll eliminate this. So it looks like this is the best. This one isn't as good because it has more formal charges. The fewer the formal charges and the lower the magnitude of that charge, the better. For example, +1 is more stable than a +2, etc. And so comparing this middle structure with this one on the right, we pick the middle one. Now, we picked the top oxygen. What if we picked the bottom oxygen? Would that, it would be the same. In fact, we do that because we have a choice here, and we typically write that other structure. Let's just write it down here. We're running out of room. We'll just write it over there. Well, maybe I'll just write it here. Right here. We do that, and we use this double-headed arrow, and we call this a what? These would be 2 resonance forms. Yeah, these are 2 resonance forms. And so it looks like, if you look at the bottom terminal oxygen, it's single, double. Single, double, single. Does it resonate back and forth? Double, single, single, double, single, double. Does it resonate back and forth? Normally when we think of resonance, we think of this oscillation, but in this case, it doesn't resonate back and forth. It's not a single, it's not a double. Do you know what it is? It's a 1.5 bond. It's the average. And the formal charge is not -1 and 0 resonating back and forth. The formal charge is -1/2 on both. And so that's called the resonance hybrid. The resonance hybrid is the hybrid structure that is the mixing of these 2 resonance forms. Have you heard this before? Yeah. Good. This is what we end up with if we use, structure based on, well, the bonding. When we look at the bonding, there are 2 theories that we use for bonding. Actually, it's pretty much 2 of the same. There's the quantum mechanical light version and the quantum mechanical full version. And so sometimes what we do is we use the quantum mechanics light version to better understand, because the quantum mechanical light version we can do by hand, and like this. The quantum mechanical, the full version, we have to do by computer, because the calculations are very math intensive. Do you recall what the names for the quantum mechanical light version of structure versus the quantum mechanical full version of structure is called? They call them both theories, but both of these theories are based on quantum mechanics. I'll give you the acronyms for the two theories. One is called VB theory, VV theory. The other is called MO theory. MO versus VB. You recall what those stand for? Yeah. MO is molecular orbital theory. Molecular orbital theory is the full quantum mechanical version. The full quantum mechanical version to the structure of HNO3 wouldn't do any of this. The full quantum mechanical version, we do the calculations, and then after we do the calculations, Schrodinger's equation, all that, we get spit out the hybrid structure. The hybrid structure, and it's more in depth than the hybrid structure, and we get a lot more information. We generate new orbitals called molecular orbitals and all that other stuff. VB stands for valence bond theory. Valence bond theory is the light version. Valence bond theory, it's a lot easier to visualize. So for example, in valence bond, this nitrogen's sp2 hybridized. And so this would be an sp2, sp3 sigma bond. And this double bond would be an sp2, sp2 sigma, pp pi bond. Do you remember all those things? And so pp pi bond, sp2, sp2 sigma, we can kind of visualize that. No? Not at all? And so the molecular orbitals are quite complex for this, but like, for example, if I look at this bond here in terms of VB theory, I'll try to draw it in the proper shape, but this would be an sp2 on that, and then we have an sp2 on the oxygen over here. Actually, nitrogen should be a little bit bigger. Yeah? And so this would be an sp2, sp2 sigma bond. There are 3 sp2 orbitals, like this. And so one of these is being used to this. And then we have 2 more sp2 orbitals on this oxygen, which have the lone pairs. When we have sp2, then there's an unhybridized p orbital on there. An unhybridized p orbital would be perpendicular to the page here. So this would be one lobe of the p. The p has 2 lobes. There'd be another lobe sticking underneath. And there'd be a p orbital here with another lobe sticking underneath. And then we have something called a pp pi bond here. If we looked at this, if we rotated this 90 degrees this way, then we can put the p orbital in profile, like this. On the oxygen and the nitrogen here, and then we can see the pp pi bond here, like this. And then we have the sp2, sp2 sigma bond here. So double bond consists of 1 sigma and 1 pi bond, and we visualize it like that using valence bond theory. But valence bond theory, this is actually the light version of quantum mechanics, not the full version. Because even though we're doing all this orbital stuff and it looks pretty sophisticated, it isn't. This is a gross simplification, because even though we're doing this orbital, we were getting the energies, the accurate or the true energies. We can only get the energies from MO theory. And the molecular orbitals look totally different. Well, in some ways they look similar, in other ways they're totally different. These are called atomic orbitals, and we're overlapping atomic orbitals. So valence bond theory is the overlap of atomic orbitals. Molecular orbital theory is the combination, that is, the mixing of atomic orbitals to make new orbitals called molecular orbitals. So we generate a whole new set of orbitals. But it's much easier to retain atomic orbitals and just overlap them than generate this whole new set of orbitals. That makes sense? So when we think about orbital diagrams, Do you remember generating atomic orbital diagrams? S, P, 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 S, P, 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 D. You know? Yeah, with the lines, 1S, 2S, 2P, 3S, 3P, 4S, 3D, 4P, right? This is an MO diagram here. So this is a little bit more complicated than MO diagram. So this is kind of the MO diagram here with molecular orbitals, not atomic orbitals, right? And so MO is a lot more intensive, math intensive, calculation intensive. You generate new orbitals with weird shapes to them, right? And so we can look at what molecular orbitals look like. That's for HNO3. Although this is not HNO3, this gives you some examples of what MOs look like. Now this would just be one molecular orbital, you know, with these weird looking lobes. But the nice thing about MOs is you get the energy levels. In valence bond theory, you can't get the energy levels. In valence bond theory, we can't do spectroscopy. That is, we can't do these electron transitions in those. In MO, we can. The MO is much more powerful, but it's not so easy. And so we usually compromise and just do valence bond, which Lewis structure is Vesper. This is all valence bond theory. And then we can do it by hand. And so, you know, when we're trying to understand properties, we want to understand the structure, you know, the composition. And so what can we do with the structure of these? And so we'll be looking at this little by little as we go along, but so we have the two resonance forms for this. Okay, then that looks okay. All right, so formal charge, this is very useful in determining which Lewis structure is going to be the most stable. A third way of counting electrons is by using oxidation states. Oxidation state, we make the opposite assumption. The opposite assumption is we assume that we have 100% ionic bonds. So let's look at counting oxidation states next. And when we divide up the electrons, we divide them up differently. So for example, with formal charge, we just did an even split. But for oxidation state, we aren't. If it's 100% ionic, there's no sharing, you know. 100% ionic means winner take all. And so, well, who's going to win the electrons, oxygen or nitrogen? So if there's a tug of war for electrons, which one is stronger? Which one's stronger is the more electronegative one. So what's more electronegative, oxygen or nitrogen? Oxygen. The most electronegative element on the periodic table is fluorine. 4.0. And so the way we count the electrons is based on how we divide them. And oxygen versus nitrogen, oxygen wins. So even though with formal charge I'm going to circle. Oxidation states I'm going to put parentheses around so we can make sure we can tell the difference. But now count how many electrons does oxygen have. Well, we'll count it like this. 2, 4, 6 from the lone pairs, plus this bonding pair. The bonding pair belongs entirely to oxygen. Nitrogen gets none of it. 8. So oxygen ends up with 8 electrons. How many did it contribute into the pool? 6. So it ends up with 2 extra electrons. Each electron is negatively charged, which means it gets an oxidation state of -2. So again, oxidation states in parentheses, formal charge, circled. Now you're thinking, oxygen, it's -1 one way and -2 another way. What we should never do is we should never compare oxidation states with formal charges. They're two different numbers. So it's like if somebody asks you, what's the biggest orange that you have in the bag, you wouldn't give them an apple, like I'll take the biggest orange and then you give them the biggest apple. It doesn't make sense because they're two different things. Well, the same thing. You can't cross compare formal charge with oxidation state. You can compare oxidation states with oxidation states and formal charges with formal charges, but we use them separately. That's because we make the opposite assumption here. Okay, how about the oxidation state of this bottom oxygen? So oxygen versus nitrogen, who wins?
Oxygen.
And then how many electrons does oxygen end up with? 8. Giving it an oxidation state of -2. So even though this one has a negative formal charge and this one has a 0 formal charge, they both have the same oxidation state, which is -2. Okay, how about this oxygen over here, the bridging oxygen?
8.
8,
-2.
-2. This nitrogen? It ends up with 0 electrons. How many electrons did it put in the pool of electrons? 5. So it lost all 5 electrons, which means it's going to be +5 in the hole, or deficit. And so this is going to have a deficit of 5 electrons, so it's going to get a +5 oxidation state. And this hydrogen? +1. All right, oxidation states are useful for determining redox properties. When we look at redox properties, redox is electron transfer. And electron transfer is going to happen between electron-rich species and electron-poor species. And so what's going to happen is electron-poor species are going to take electrons from electron-rich species. That's what's going to happen. What's electron-rich and electron-poor is relative. So just because I have a +1 doesn't necessarily mean that's electron poor. It could just be happy as is. Just because I have a -2 doesn't mean it's electron rich. In fact, for oxygen, -2 is kind of its normal charge because oxygen wants 2 extra electrons to complete its octet. And so oxygen with a -2 is quite stable. And you wouldn't consider that electron rich, it would just be stable as is. +1, and so we compare it. You can't even, like I said, that you can compare oxidation states with oxidation states, but you can't compare an oxidation state on one element versus an oxidation state on a different element because the numbers are relative to that specific element. And so normally what we do is we compare the oxidation state of one element in one compound with the oxidation state of the same element in a different compound. So let's compare it like the water. Would you say water is a pretty stable chemical?
Yeah.
Pretty unreactive? Yeah, you could drink this stuff. It's not going to kill you. Well, if you don't drink too much, it's not going to kill you. And so water is a pretty stable chemical. What are the oxidation states in water? Remember, winner take all. +1 on hydrogen. So what that means is +1 is kind of a normal average charge on hydrogen, stable. What is the oxidation state on oxygen? -2, which means in the grand scheme of things, a -2 is a very common charge on oxygen, and I don't expect that to be rich or poor. I expect that just to be good, other than stable. But if we look at nitrogen, now, looking at nitrogen, what do you think about that? +5. What does that sound like? Pretty poor or pretty rich to you? It sounds pretty poor. Poor being it doesn't have many electrons. And so nitric acid overall would be an electron-rich compound or an electron-poor compound overall. Looking at all the atoms, I'd call nitric acid electron-poor. Now, electron-poor species are what we call oxidizers. Electron-poor species want electrons, and they're going to take electrons from other species. And so, nitric acid, based on the oxidation states, should be a pretty good oxidizer. We can look at some other oxidizers as well. And so, oxidation state is very useful in terms of redox properties. Sometimes oxidation states also in formal charge helps us. Formal charge helps us in terms of acid-base. Formal charge is very useful in acid-base and Lewis structures. So, do you know what makes a good Bronsted base? What makes a good Bronsted base is a good proton acceptor. What charge is the proton? Positive. And so what do you expect? The more negative an atom is, the better it's going to be at attracting a positive charge, right? So if I'm thinking about acid base, and let's say, because I know resonance forms, when I have resonance forms, it's neither, right? The true structure is a hybrid, actually. But let's just pick one of these resonance forms. Let's just focus on this form and freeze it. Actually, we can't freeze it, but let's say we have this form. Which of these oxygens do you think is a better base? The top oxygen or the bottom oxygen? The bottom oxygen would be a better base. Why? Because it's got a negative formal charge. It's got that extra electron. That negative formal charge is going to mean it's going to be more attracted to positive charge, and the proton's a positive charge. And so what that means is this is a better base than this and this. This has a 0 formal charge. Do you see that? And so formal charge, not always, but can help us with acid-base properties. Another thing that can help us is this. Like, for example, this hydrogen we call acidic. I asked you what atom that hydrogen bonded to, and we picked the oxygen being the more electronegative of the two. But what if we have this? This is an acid. Is this an acid? We don't normally think of methane as an acid, do you? Now, methane, the natural gas, we don't normally think of this as an acid. Why not? It's got 4 hydrogens. I mean, 4 hydrogens compared to 1 hydrogen here, shouldn't this be a better acid than this? With 4 hydrogens, would this be a better acid? And it turns out, no, what makes an acid? What makes an acid is we want the hydrogen to be as positive as possible. But when you look at the formal charge of this hydrogen is 0. What is the formal charge of this hydrogen? The formal charge of this hydrogen is 0, so the formal charges are the same. So does that mean they're the same acidity? And so what we have to do is we have to use a combination of all these approaches here. We use a combination of all these approaches to come up with an idea of this. And when we do this, think about this. Think about the electron cloud here. If we have a nitrogen in the +5 oxidation state, that's going to want to pull in as much electron cloud density towards it as possible. And so this is what's going to happen. This electron, this nitrogen in the +5 oxidation state is going to take this electron cloud and kind of distort it towards itself, like this. And it's going to polarize the electron cloud, right? And as this nitrogen sucks electron density away, normally oxygen is more electronegative, but this is nitrogen in the +5 oxidation state, which means it's poorer than usual. And that's going to suck electron cloud density away from this hydrogen even more. And so what that means is that it makes this hydrogen more positive. Now, we look at the oxidation state of the hydrogen. The oxidation state of the hydrogen is +1. Now, let's look at the formal charges here. All the formal charges are 0. What are the oxidation states, however?
The carbon is -4.
Yeah. The oxidation, the carbon is -4. Is that rich or is that poor? That's rich. This carbon is very electron rich. How about the hydrogens? They're all +1. But even though these are all +1, there's a big difference here. You look. And the big difference is, yeah, this hydrogen is +1, but when you look at what this is bonding to is sucking the electron density away from this hydrogen. Over here, when we look at this hydrogen, this carbon is very rich. So it's not sucking away all the electron cloud density away from the hydrogen. And so there's the fourth method of counting. The fourth method of counting is this. And I've been talking for a while, but the fourth method of counting is between the two extremes. You know, let's say you go out in the forest. You go out in the forest and there are a lot of trees. Let's say there are thousands of trees. Do you just pick one tree and look at it? You look at this tree, oh, it's 75 feet tall, right? No, what you want to do is you want to see the extremes on one end and the extreme on the other end. So what we're looking at is we're looking at the extreme on one end and the extreme on the other end. What the reality is often is it's between the two extremes. And between the two extremes we call polarity, you know, like bond dipoles. Polarity is between 2 and 3. And so let me talk about polarity here, because polarity gives us clues as to the chemical properties as well. And polarity would be something like this. When we look at nitric acid, there are different ways of determining why that hydrogen is fairly acidic. One way of determining this is due to something called the inductive effect. Do you guys recall what the inductive effect is? The inductive effect will explain the difference between nitric acid and nitrous acid. What's the difference in oxygens? Nitric acid has 3 oxygens. How many oxygens does nitrous acid have? 2 oxygens. So let's go ahead and draw the Lewis structure for nitrous acid. Like this. So the inductive effect says this. If you have terminal oxygens, the terminal oxygens are like blood-sucking atoms. And these blood-sucking atoms are sucking the electron cloud density away from the nitrogen. Like this. You see the electron cloud is being sucked away from the nitrogen. That means nitrogen is going to be more electron poor, which in turn is going to suck more electron density from the oxygen. And that's going to make this oxygen even more electron poor than it normally is, which is going to suck electron cloud density away from the hydrogen. Now the hydrogen is going to lose electron density. What's going to happen is the hydrogen is going to have a charge between 0 at one extreme and +1 at the other extreme. And we don't know what that charge is. We can calculate it using quantum mechanics. Since we don't know what that charge is, we assign it a delta, meaning it's a charge between 0 and 1 in this case, you know, whatever the two extremes are. And so we call it a delta plus. We can calculate what delta is using quantum mechanics. And then the oxygen is going to be a delta minus. And we set up a polar bond. This is called a polar covalent bond. And that makes this hydrogen more acidic. Whereas over here, we don't have this going on. Over here, these are called non-polar covalent bonds. And in fact, when you look at electronegativity, carbon is a 2.5, hydrogen is a 2.1. The electronegativity difference is 0.4. 0.4 electronegativity difference means that, the delta plus here is so small, it's negligible. And so if you're a base, let's say you're hydroxide. Hydroxide is looking for positive charge. Hydroxide is a great base. It has a negative formal charge on oxygen. So if you're hydroxide, you're looking for positive charge, you're going to see it here. You're going to attack that hydrogen because this hydrogen has positive charge, right? If you're hydroxide, are these hydrogens going to be very attractive? No, these hydrogens aren't going to be attractive at all because these hydrogens are going to have a very small delta plus because the bonding is more covalent than ionic. So the formal charge would be more accurate than the oxidation state in this case for the charge. And so this is a non-polar covalent bond. So what we do is we do a mix, we analyze all these numbers here and we take a step back and look, and then we use them differently. And so it depends on how many terminal oxygens we have here. Here we have 2 terminal oxygens, here we only have 1 terminal oxygen. So the inductive effect is going to be less. The inductive effect is less, meaning that the delta plus that results on this hydrogen is going to be smaller than the delta plus resulting. So we call nitrous acid a weak acid. Nitric acid is a strong acid. We can also see this inductive effect based on oxidation state. Because when we look at nitric acid, the oxidation state of nitrogen here is +5. +5 is very electron poor. It's sucking the electron cloud into it. What's the oxidation state of this nitrogen? Winner take all. What's the oxidation state of this nitrogen? +3. So do you see that more electron cloud density is going to be sucked into the +5 versus the +3, making this one less positive, this one more positive. Does that make sense? So we use a combination of things to analyze our structures to get a better idea of how that might behave. Now, one of the things, though, that we see is this. If it's electron poor, we call it an oxidizer. The methane, however, is not an oxidizer because these hydrogens are happy at +1. Methane is electron rich. Electron rich species we call reducers. And so methane is an excellent reducer. Reducers are fuels. Oxidizers for the oxidizers. So we'll take a break here. Let's start up again. All right, hydroxide is an excellent Bronsted base. It seeks out, acidic hydrogens. Acidic hydrogens, the more positive the hydrogen is, the more acidic it is. And so we call these two acidic hydrogens, and this would be a better acidic hydrogen than this one. These would be non-acidic hydrogens. So if hydroxide came, hydroxide wouldn't be so interested in these hydrogens because they're not very acidic. What about water? What would be a better base, hydroxide or water? So if I have water here, water can also try to take this proton, because when we look at water, and we'll just do the polarity. Looking at the polarity, these are polar covalent bonds. Oxygen is more electronegative. This oxygen is going to have a delta minus. So this delta minus on oxygen is going to be attracted to this delta plus on hydrogen. And so what we can have is this. Now we're going to look at it in both ways. We're going to look at this in Bronsted-Lowry. In Bronsted-Lowry, we want a proton transfer. That is the hydrogen transfer from here to here. In Lewis, we look at electron pair donor. And so Lewis, we look at this electron pair attacking this hydrogen. And so this electron pair, the hybridization, do you know what the hybridization on this oxygen is? sp3. There are four groups. Four groups is spp, sp3. So we have an sp3 lone pair here, and this is going to be an sp3 sigma bond. And so this sp3 lone pair is going to get pushed into this s orbital and kick these out. And so what we'll end up with is an sp3 s sigma bond here. And so what that's going to result in is this. We're going to have the proton transferred, and we're going to make, let's see, a little black here. We're going to make this, HH, in other words, hydronium, H3O+. Now, when we look at the charges here, look at this oxygen. What's the formal charge on this oxygen? Formal charge. The formal charge on this oxygen is +1. The formal charge on the hydrogens? 0. Now, when the formal charges don't add up to 0, there's going to be a net charge, and this is going to be an ion. So if we add up all the formal charges, we get the net charge. The net charge we write outside like this. We put some brackets here. And so this is just H3O plus with the positive charge localized on this oxygen here. Okay, and then we'll be left with this. These bonding electrons are now going to be converted into lone pair. And what are the formal charges here? Well, this oxygen is 0, the nitrogen is plus. This oxygen is minus, and this oxygen is minus. So now add up all the formal charges. What's the net charge of this? If we add up all the formal charges, the net charge is going to be minus. And so we end up with hydronium, H3O plus, and nitrate, NO3 minus. Now, is water a weaker base or a stronger base than hydroxide? What would your guess be? What would be more reactive, Sodium hydroxide or water? Yeah, sodium hydroxide. In fact, sodium hydroxide is used as drain cleaner. It's called lye. You can buy it at the supermarket. Would you drink water? Sure. Would you drink sodium hydroxide? Drain cleaner? No. I'm going to drink this stuff. And so, you expect water to be much weaker. But water is plenty strong enough for this. So water can pretty much take all the hydrogens off nitric acid. Now, if water were to try to do the same thing with nitrous acid, it won't. Nitrous acid is going to fight off water more. And so water can only partially ionize weak acids. However, water can fully ionize strong acids. And so we have a name for this. And the name for this is electrolyte. Strong acids are strong electrolytes. Strong electrolytes are completely ionized or completely hydrolyzed in water. Weak acids are weak electrolytes. Weak acids are only partially ionized or partially hydrolyzed in water. So nitrous acid is a weak acid. It's not going to completely react with water. Nitric acid is a strong acid. It completely reacts with water. And so when we put nitric acid in water, we expect it to completely dissociate into ions. The hydronium ion or the hydrogen ion and nitrate ion. When we put nitrous acid in water, we only expect it to partially dissociate because it's a weak acid. And the amount of dissociation depends on how strong it is. The stronger it is, the greater the dissociation. The weaker it is, the weaker the dissociation. Now, all strong acids are completely ionized or dissociated in water. And so, and the weak acids, we have different grades. The stronger the weak acid, the more. The weaker the weak acid, the less it's ionized or dissociated. So one thing about nitric acid is it's a strong acid. And so a strong acid can react with a weak base like water, or it could react with a strong base like hydroxide. Hydroxide has no problem. In fact, hydroxide has no problem taking the hydrogen off nitric acid, and hydroxide would have no problem completely stripping all the hydrogens off the weak acid, nitrous acid. Does that make sense? Because hydroxide is a strong base. Now, we're going to take a look at the reactivity, but we're going to look at reactivity just in terms of reactivity. We're not really going to analyze this based on structure or properties. We're going to analyze it based on using a chart. And so let's take a look at the acid-base chart. And this is the Brownsville acid-base chart. And we're going to look at how we can figure out the chemical properties based on looking at a chart. And so, we try to put in all these factors because not everything's on the chart. If something doesn't occur on the chart, how do we analyze it? Well, we analyze it like we just did. If nitric acid wasn't on the chart, we'd start thinking about the structure and how the electron densities range. So here's nitric acid. One of the things we know about nitric acid is a strong acid. Strong acids undergo complete acid ionization in water. What are some of the other strong acids that we see? Well, the other strong acids, what's this one? Well, hydrogen chloride we usually call as a gas, but if it's dissolved in water, we don't call it hydrogen chloride, we call it, HCl is called hydrochloric acid. And so hydrochloric acid is also a strong acid that's completely ionized in water. This one's called hydrogen bromide or hydrobromic acid, hydrogen iodide or hydroiodic acid. And now you learned, you were supposed to memorize 7 common strong acids. Which one's missing? Can you tell which one's missing? If you take perchloric acid and you lose 1 oxygen, what do you form? If you have perchloric acid and you lose 1 oxygen, so it's HCl4 goes to HCl3, what's that called? It's chlorate, and the acid would be named chloric acid. So chloric acid is missing from this. Chloric acid is somewhere in here. There. So the first thing is this. Water is plenty enough, strong enough to completely strip the hydrogens off all these acids. So let's say I look at this and I see, oh, HCl is stronger than HNO3. Well, these are in what we call the gas phase. And so in other words, HCl is stronger, so it's a little easier to pluck the hydrogen off, HCl, than it is to pluck off the hydrogen off HNO3. But water has no problem. For water, it just requires slightly more effort to take the HNO3 than the HCl. Slightly less effort for HBr, slightly less, but it's plenty strong. You can ionize all of them. This is like if you have a fruit tree. If you have a fruit tree, any piece of fruit within reach is easy pickings, right? So for example, the easiest would be like perchloric. So perchloric would be the lowest hanging fruit. The lowest hanging fruit is going to be easiest, perchloric. But, a little bit higher is nitric acid. Nitric acid is going to be a little harder, but it's within reach. And so if it's within reach, you can pluck every single piece of fruit there. But when we start to go to phosphoric acid you have to jump up to grab. If you happen to jump up and grab it, then maybe you get 80% of them. And so in phosphoric acid, it's not 100% ionized, it's only about 80% ionized because water can't get that remaining 20%. as the acids get weaker and weaker, it gets harder and harder for water to remove that. So if we go to acetic acid, it's only about 0.1% of the hydrogens are removed by water. So this is only about 0.1% ionized. And so this is much more difficult to remove. And so that brings up, when we use this chart, there are two charts we use. This is called the gas phase, and then the aqueous phase. In water, all the strong acids have the same strength. So if you have HNO3, all of that's going to go to hydronium. So if you have 1 molar HNO3, we generate 1 molar hydronium. But the same thing with HCl. If we have 1 molar HCl, we generate 1 molar hydronium. No different. And so all these yield the same amount of hydronium, except for H2SO4, which we'll talk about later, but all these give the same amount of hydronium, therefore all of them have the same strength in water. And that's called the leveling effect. And so even though HClO4 is at the top and HNO3 is at the bottom of the strong acids, they're all the same strength, because even if we have HClO4 in water, it's still going to yield 100% hydronium, just like HNO3. Okay, so these acids have the same strength in water. Now, once we go to weak acids, then these are going to be graded. So, for example, phosphoric acid is stronger than nitrous acid. Nitrous acid is stronger than carbonic acid. And so these are going to be graded as is, whether they're in gas phase or aqueous phase. Okay, but remember, this is called the leveling effect of strong acids. All the strong acids have the same strength in water. Okay, let's go down the list. The weakest acid on this list is methane. Heck, we don't even think of methane as an acid. You know, is a base going to be attracted to any of those hydrogens? No. This is weird. However, there are some unusually powerful. What kind of base would you need to attack methane? You would need an awfully powerful base. And so let me show you how this chart works. And so let's take a look at an acid here. And talk about the conjugate relationship. If the acid is strong, its conjugate base is weak. These acids are extremely strong, and therefore these conjugate bases are extremely weak. In fact, these conjugate bases are so weak, if you read here, they do not undergo base ionization in water. What that means is they're so weak, they're neutral in water. You know, they're not going to do anything to water. Water is an unusual chemical because water is what we call amphoteric. It can act either as an acid or base. And so, like chloride isn't even thought of as a base, nitrate's not thought of as a base. None of these are thought of as a base. These are all thought of as being neutral ions. Now, the stronger the acid, the weaker the conjugate base. And so if we compare phosphoric acid, the conjugate base of that is dihydrogen phosphate. If we compare carbonic acid, the conjugate base is bicarbonate or hydrogen carbonate. Well, bicarbonate is going to be a stronger base because this is a weaker acid, and this is going to be a weaker base because this is a stronger acid. There's a seesaw relationship. So the stronger the acid, the weaker the base. And so we can go down here. And so on the left side, we have the acid strength chart. On the right side, we have the base. At the top are the extremely weak bases. These are so weak they're considered neutral. And then we go stronger and stronger as we go down. Now we have the incredibly weak acid, methane. Now it's so weak, nobody considers methane an acid. But the conjugate base of methane, so if methane lost a proton, a hydrogen plus, it would form methide. And methide, this is like the ide. You remember, like it's chloride, but it's methane. It's the anion, methide. This is an extremely powerful base. This is the most powerful base on this chart. And then we have hydrogen we don't think of as an acid either, but If it acted as an acid, it would form hydride. Ammonia we normally think of as a weak base, but if ammonia reacts as an acid, it forms amide, the ammonium anion. We have ethanol. Ethanol is an alcohol. We don't normally think of that as an acid, but if it did react, it formed ethoxide. These bases are so powerful that all these bases will attack water. Water will act as the acid, and these bases will strip the hydrogen off water. And therefore, all these bases are essentially equivalent in water. This is the leveling effect of strong bases. So let me summarize it. The strongest base that can exist stably in water is none of these. All these are too powerful. They're automatically going to react with water to form hydroxide. Hydroxide is the strongest base that's stable in water. Anything stronger than that will attack water. The strongest acid that exists in water stably is hydronium. None of these acids exist in water. All these acids will be attacked by water. And what do they form? They all form hydronium. Hydronium is the strongest acid that exists in water. Hydroxide is the strongest base that exists in water. Okay, now let's do some chemical reactions here. So let's look at hydrogen sulfate or bisulfate ion here. Okay, this can be an acid, and if it acts as an acid, it's a proton donor. So a base comes along and tries to strip off this hydrogen. Now we can think, what will this react with? Will this react with sulfate? Sulfate's a base. So can sulfate take that hydrogen from bisulfate? In other words, look at this reaction. If I have bisulfate versus sulfate, then I have essentially two sulfates fighting for the hydrogen. So if I have a tug of war, a sulfate on one side, a sulfate on the other side, a hydrogen in the middle, which sulfate will win the tug of war? The left sulfate or the right sulfate? Which one will win? Well, neither will win, because what will result will be a tie. Do you see that? Sulfate versus sulfate, there's going to be no reaction. Because if this one wins, what do we form? Well, we form sulfate and bisulfate. If this one wins, what do we form? We form bisulfate and sulfate. You see, it's going to result in a tie, no reaction. So what that means is, if I want bisulfate to react, I need a more powerful base than sulfate. So what is a more powerful base than sulfate? Is it water? So if water attacks that, will it be successful in plucking off that hydrogen? And we'd say no, because water would be weaker. Remember, this is upside down. The strongest base is at the bottom. And so we need a base stronger than sulfate. And so what is a base stronger than sulfate? Dihydrogen phosphate. And so if I take bisulfate and react it with dihydrogen phosphate can pluck that hydrogen off. When dihydrogen phosphate plucks that hydrogen off, it forms phosphoric acid. And bisulfate goes to sulfate. What else can do that? What else can do that is fluoride. Fluoride's even more powerful, right? And so if fluoride attacks bisulfate, fluoride will pluck off that hydrogen. What forms? Well, when fluoride plucks off that hydrogen, bisulfate goes to sulfate, and fluoride goes to hydrofluoric acid, or hydrogen fluoride, whatever you want. Nitrite is powerful enough to pluck it off, right? So if nitrite plucks it off, we form nitrous acid and sulfate. So any base stronger than sulfate will. Acetate will pluck it off. Bicarbonate will pluck it off. Hydrogen sulfide ion will pluck it off. Do you see how it works? All right, so going to nitric acid. Nitric acid is a powerful acid, it's strong. So any base stronger than nitrate will pluck off the hydrogen. So if I'm at nitric acid, will water pluck off that hydrogen? Yes. Sulfate? Yes. All these will pluck off. So what's the chemical property of nitric acid? Well, the chemical property of nitric acid, in terms of acid-base properties, is this. Over here. equal to and stronger than water. So what that means is we're going to have a long list. Here. Now, there are two ways of thinking about this. One is this. Nitric acid consists of the acid H plus, or hydronium, and the base nitrate. Remember, this base is too weak, too weakly basic, therefore neutral. So basically, it's just hydronium. Well, what reacts with hydronium? Well, anything stronger, if we already have it. So water, in order to make hydronium, we need water. And so water is already, or if we just leave it as H plus and HNO3, then water and anything stronger. And so we have a long list of bases that we can react with this. Okay. Let's try another example. If we look at hydrocyanic acid, or hydrogen cyanide, HQ, hydrocyanic acid, will any old base react with hydrocyanic acid? So let's say, for example, will cyanide neutralize hydrocyanic acid? No, we're going to get a tie. How about bicarbonate? Will bicarbonate neutralize hydrocyanic acid? No. Will carbonate react with hydrocyanic acid? Yes. Will hydroxide react with hydrocyanic acid? Yeah. And so anything stronger than cyanide will react. And so that means hydroxide, sulfide, ethoxide, amide, hydride, methide. All will react with HCN. See that? So that gets to the point where, here, okay, if we're at methane, will methide react with methane? No, that's going to be a tie. So what we need, in order for methane to react as a acid, we need a base stronger than methide, but methide's the most powerful base on this chart. But the situation is, are there more powerful bases than methide? And the answer is yes, there are. There are bases called superbases, and there are acids that are more stronger than HCl4 called superacids. In fact, over at USC, there's a professor there, Professor George Olah, who has passed away, but he won the Nobel Prize in Chemistry for his work with superacids and superbases. Because think about this. If you have a superbase that can pluck a proton or hydrogen plus off methane, then you end up with methide. Methide's very reactive, unstable, right? And so what he was doing was he was trying to link up the carbons. So if he could link up carbon hydrogens and get longer chains of carbon, then he could make hydrocarbons, and hydrocarbons would be like synthetic fuels. And so he's trying to take methane and make it into synthetic gasoline, by adding additional carbon atoms and making branches and that kind of stuff. And so that was some of his work, in addition to other things. And so there are more powerful bases called superbases, and there are more powerful acids called superacids. And so in order to make this, and methane normally is not going to react, it's only under very rare circumstances that you get it to react, but you could. Same thing with ammonia. Ammonia is a weak base. But how can you get ammonia to react as an acid? You react it with what? What would get ammonia to react as an acid?
A base stronger.
A base stronger than?
Stronger than
Yeah, NH2 negative is called amide. A base stronger than amide. And so in order to get ammonia to react to form amide, we could try using hydride. And so ammonia plus hydride, what does it make? Well, hydride goes to hydrogen, ammonia goes to amide. So we form amide and hydrogen gas. If we had methide, then yeah, we could do that. We take ammonia and methide. What would form? Well, methide will pluck a hydrogen off there to form methane, and this will lose a hydrogen to form amide. So this is how we're going to use the chart, and using the chart, we can quickly determine the reactivity of these. This is easy because it's strong acid, so pretty much all the bases will react with this, except the super weak bases. The super weak bases would be these. You know, would chloride neutralize nitric acid? No, chloride pretty much is not going to neutralize any of these. You know? Would chloride neutralize HBr? Yes, you would think chloride would neutralize HBr because chloride's a more powerful base than bromide. However, you have to remember the leveling effect. The leveling effect says all these are equal. All these are equal. And so all these are going to be equal in terms of base strength, which means, you know, chloride, bromide, iodide, bisulfate, perchlorate, none of these will neutralize any of these. Does that make sense? And so that's the one tricky thing about this chart. Otherwise, the chart is okay. And so that's acid base. Nitrate, you know, not going to neutralize anything. It's too weak to be basic. And then we got the H+, or just look at it in terms of HNO3. Now, the next thing we're going to look at is redox. And we already know nitric acid is electron poor. What other species are electron poor? Oxidizers are all electron poor, and this chart has all the oxidizers on the left. Oxidizers are electron poor, reducers are electron rich. This chart is upside down from the chart in our book, in our class. The reducers are electron rich, and the reducers occur on the right side of this chart. If you look at this, this is lithium, potassium, calcium, sodium, magnesium, aluminum. You know what this looks like? This looks like the activity series. If you remember the activity series from like chapter 5, lithium is at the top. It's the most reactive. In other words, lithium is the most electron rich out of all these species. Metals are electron rich. And so let's take a look at this chart for a moment here and get our bearings. Okay, the same thing happens with this chart. There's a conjugate relationship. And so what we have is we have an oxidizer-reducer conjugate pair. If the oxidizer is powerful, the reducer is very weak. If the acid is powerful, the conjugate base is very weak. If the oxidizer is very powerful, the conjugate reducer is very weak. So in other words, fluorine is the most electronegative element on the periodic table. It really wants an electron. That makes it a powerful oxidizer. What's the oxidation state of fluorine? The oxidation state of fluorine is 0. And so, you can't compare, you can't compare a 0 on one element with a 0 on fluorine. They're totally different things. We know what a 0 means in the context of fluorine means it's electron poor. And so fluorine's electron poor, it wants electrons to form fluoride. So fluorine is a very deadly gas. Fluoride people use to brush their teeth with, right? And so this is in toothpaste, it's not going to kill you. If you try to brush your teeth with fluorine gas, it could kill you, because basically it's going to catch your mouth on fire. It's such a powerful oxidizer, it'll just start combusting all your tissue. Your tissue is electron rich in that sense. So anyway, this is the conjugate. So the most powerful oxidizer, the weakest reducer. Oxidizers take electrons. Reducers give up electrons. Okay, so we're going to look at patterns later, but let's take a look at the top 5 oxidizers. The top 5 oxidizers on the chart, fluorine. What's O3 called? Ozone. Ozone's a powerful oxidizer. If you've ever inhaled ozone, it's much more reactive than O2, oxygen gas. This one, S2082 minus, this one's very weird because when you do the oxidation states, sulfur comes out as +7. Ozone's 0, by the way. Sulfur and a +7 is a bit weird because how many valence electrons does sulfur have? Sulfur is right underneath oxygen, so sulfur has 6 valence electrons. Here it's +7, so that means it's lost all 6 valence electrons plus a core. But it turns out it's not that way. What happens is that's assuming oxygen's -2. In this case, 2 of the oxygens are -1. We see -1 oxygens. -1 oxygens often occur in this type of bond. Let me give you an example of it. Here. Do you know the name of this stuff? This is H2O2, right? Hydrogen peroxide. Hydrogen peroxide is very unstable, and it's a good oxidizer. Hydrogen peroxide is a good oxidizer because not because of the formal charges. The formal charges are all 0. It's because of the oxidation states. The max positive oxidation state on hydrogen is +1. We can't go to +2. If we could go to +2, then oxygen would be -2. But since we can only go to +1, then each oxygen is -1. Because this whole thing has to add up to 0. And so this is oxygen. It's not quite there at the octet, in that sense. Although when you look at it, it does obey the octet rule. And so it's got -1. It would like to be -2. And so that makes hydrogen peroxide pretty reactive. And if you look at number 4 is hydrogen peroxide. Hydrogen peroxide is a powerful oxidizer. But it's not the 3% hydrogen peroxide that we have at home. It's the more powerful stuff, like the 30% hydrogen peroxide. The 30% hydrogen peroxide or the 50% hydrogen peroxide is very dangerous. In fact, it's used for different things, like for hair and for gardening. It's used. And there's a story it's online. It's a story. It's in the FAA. This was pre all the security checks, but there was a person, I think in San Diego, who had purchased some hydrogen peroxide. I think it was like 50% hydrogen peroxide, and they put it into like a milk jug container, milk carton, plastic. And then they put it inside a plastic ice chest and then wrapped it up with duct tape. And then they convinced the person at baggage check to check that as baggage on a flight. And what happened was, this was a flight from, I think, San Diego to Sacramento. What happened was the hydrogen peroxide ate through the plastic milk jug and then ate through the ice chest and then started dripping on a fabric luggage suitcase. And it started to combust, started to catch on fire. And then smoke started filling the cabin, and then they did an emergency landing. But they're lucky. They're lucky because, the hydrogen peroxide dripped onto the fabric. But what would happen if the hydrogen peroxide dripped onto the metal frame of the airplane? Aluminum, that's an oxidizer. Oxidizers, hydrogen peroxide is oxidized, electron poor, wants electrons. Well, aluminum is electron rich. Aluminum is close to lithium, the most powerful reducer on the chart. And so if that hydrogen peroxide dripped onto the aluminum, it would just eat it right up. Okay? And so I think they were quite lucky. Although probably the luggage was, encased in another barrier to prevent it from ever hitting the aluminum structure of the airplane. But anyway, just good. Nobody was hurt in that incident. All right, there's lots of patterns in here. We'll look at the patterns later. Normally we analyze structure, composition, and properties, but for right now we're just going to use the chart. And we're going to use the chart to just figure out the chemical properties quickly. And so do you see the top 5 were what? Fluorine, ozone. This one you don't need to know the name. Hydrogen peroxide and what's this called? well, actually, let's just read these off. MnO4 minus. Do you remember that one? That one's not off the chart. There are some that you just have to plain old memorize. And this is a common one that you just have to memorize. MnO4 minus is called, what? Close. Permanganate. Permanganate. So permanganate's a powerful oxidizer. Number 5. This one, PbO2, is called lead-4 oxide. Lead-4 oxide is the oxidizer in car batteries. You know, your automobile battery will have lead-4 oxide. This, chlorine. So chlorine is weaker than fluorine. This one, Cr2O7 2 minus. Chromate is CrO4 2 minus. Cr2O7 2 minus is called dichromate. Dichromate. So these ones you need to memorize. You need to memorize permanganate, dichromate, chromate, oxalate, acetate. You know, those don't fall on the chart. There's no pattern. The best way to memorize those is just write them repeatedly. Then we have manganese 4 oxide, O2, iodate. And this is iodate with H+. Iodate with H+ is called iodic acid. Bromine. And then what's this? Nitrate with H+. Do you know what nitrate with H+ is called? Nitric acid. So nitric acid here is an oxidizer. Is it in the top 5? No, but you know, it's in the upper part, so it's a moderately strong oxidizer. And so what we think of, in addition to its acid-base properties, nitric acid has redox properties. Nitric acid is electron poor, and it's going to react. Now, what is it going to react with? Well, it's going to react with a reducer. And so this is the same type of thing that we did for the acids. If nitrate and H+ tried to oxidize nitric oxide or nitrogen monoxide and water, will one side win? Okay, so if nitric acid got in a tug of war with NO and H2O, it would be a tie. It would be a tie. Do you see that? Just like the acid and base, they're at the same level. It's a tie. So in order for nitric acid to oxidize, it has to be a stronger reducer than NO and H2O. So for example, with nitric acid oxidize bromide. Can nitric acid oxidize bromide? Well, is bromide more powerful than this or weaker than this? It's weaker because on the right side, the most powerful is at the bottom. On the left side, the most powerful is at the top because of the conjugate relationship. Conjugate relationship says strong, conjugate weak. You know? If we're looking at the bases, if the base is strong, that means the conjugate acid is weak. And so what this means is nitric acid and bromide, no. No reaction there. We need something stronger than this. Is silver stronger? Yes. So nitric acid will react with silver. Will it react with iron too? Yes. Okay, so if nitric acid reacts with silver, it forms silver ion and NO and H2O. If nitric acid reacts with iron 2, what does it form? It forms iron 3 and NO and H2O. If nitric acid oxidizes peroxide. Normally peroxide is thought of as an oxidizer, but peroxide is like water. Water is amphoteric. Water, it can act either as an acid or base. It occurs on both sides of the chart. Hydrogen peroxide is amphoteric for redox. We don't call it amphoteric, there's no special name. It occurs on both sides. So normally we think of hydrogen peroxide as a powerful oxidizer, but it's also a weak reducer. And so hydrogen peroxide itself can be oxidized by nitric acid. So if nitric acid oxidizes hydrogen peroxide, what forms? O2, H+, and NO and water. And so we can do that. And so what will nitric acid oxidize? Well, a nitric acid will oxidize anything, any reducer stronger than NO and water. And so as far as, this is acid base here. So as far as chemical properties go, we look at 3, acid base. And then 2, redox. And so HNO3 will oxidize any reducer stronger than NO and H2O. We can list those out if you want. What are they? Well, silver, iron 2, hydrogen peroxide, iodide, copper metal, silver dioxide, tin 2, H2S, H2, PB, tin, iron, zinc, etc., etc. And some of these occur in sequence. So for example, this, if nitric acid oxidizes iron, what forms? If nitric acid oxidizes iron, then we form iron 2. But if we form iron 2, we end up here. And then nitric acid can oxidize iron 2 and will form iron 3. Do you see that sequence? And so nitric acid will take iron metal all the way to iron 3 in 2 steps. The same thing with tin. If we have tin metal, we go to tin 2, and from tin 2, we can go to tin 4. And so we could have multiple steps there. So any of these metals are good. But will nitric acid oxidize silver? Actually, it will oxidize silver. Will it oxidize chloride? Let's say I want nitric acid to oxidize chloride because I want to form chlorine. So I take my nitric acid, oxidize chloride to form chlorine. Is that going to work? No. That's going to fail. And so we do that. All right, so that's redox, and this is how we use the redox chart. We can do the same thing with reducers as well. You know, reducers, we look at what we need to oxidize. So let's say I want to oxidize, iron metal. Iron, or actually here. What can I use to oxidize iron metal? Could I use the zinc 2 to oxidize it? No, because it's not powerful enough. I need an oxidizer more powerful than iron 2. Will iron metal be oxidized by tin 2? Yes. Will iron metal be oxidized by H+? Now, H+ is what we call acid. This acid is a very special acid. You know why this acid is a special acid? Is because all acids have H+. All acids are oxidizers. And so most acids are going to have this string, H+. But some acids, the anion is an even more powerful oxidizer than the H+. And so these acids we call oxidizing acids. These are special acids because of that anion is very electron poor. And so what are these special acids? Well, this is called a mineral acid or just a regular acid. The special acids would be like this. This is sulfate and H+. Sulfate and H+ makes sulfuric acid. Sulfuric acid is an oxidizing acid. It's more powerful than a normal acid. A normal acid is just H+. So sulfuric acid can oxidize more things. We call it an oxidizing acid. What else is an oxidizing acid? Nitric acid is an oxidizing acid. Here. Right? It's one of the most common. Iodic acid is an oxidizing acid. Here. Etc. There are more. Perchloric acid, although perchloric acid is not on this chart, it's a very powerful oxidizing acid. we can tell because of the oxidation state. Perchloric acid has an oxidation state of +7 on a chlorine, which is extremely high. But most acids fall right here. So you can just take a typical acid and you can oxidize iron with that. Here. So those. Now, let's try to do the same thing. Let's try to dissolve copper metal. Can we dissolve copper metal with a typical acid? No. But we could dissolve copper metal with an oxidizing acid like nitric acid. And so copper metal doesn't dissolve in most acids. But if we have an oxidizing acid like nitric, no problem. Will silver dissolve in most acids? No, silver won't. But will it dissolve in sulfuric acid? No, sulfuric acid is an oxidizing acid, but sulfuric acid is too weak. To dissolve silver, we need a more powerful acid like nitric acid or iodic acid. Here, you see that? Okay, so that's redox. We're going to use the chart. This is just the data. You know, in scientific method, we get our observations, and then we start thinking about these observations and looking for patterns. Well, we're just taking the observations now. These are the observations of chemical reactivity. Later on, we'll think more about it in terms of structure and whatnot. Okay, the last type of reaction that we look at is the metathesis reaction. So let's talk about that here and look at what types of metathesis reactions these undergo. Okay, I have, oh, shoot. Talking to this hospital. Information. So, okay, so we have acid-base, redox, and metathesis is the final reaction type. Metathesis are favorable ion combinations. When we do favorable ion combinations, these are like double replacement reactions. Do you remember doing double replacement reactions? In double replacement reactions, you swap the ions and see if that's a good pair. So you're comparing the existing pair versus the swap pair. So you're changing partners. And if you change partners and that works out to be better, that is, they like each other more, then you get a reaction. So what types of ions like each other more? The ones that precipitate. So if you swap the ion partners and it precipitates, that's a good combination. Or if you swap the ion partners and it forms a gas and effervesces out, that's a good combination, right? Or if you swap the ions and you go from a stronger acid to weaker acid or a stronger base to weaker base, that's a good combination. Because in a strong acid, the H plus and the nitrate don't really stick together. You know, they ionize. Versus a weak acid, like acetic acid, the H plus and the acetate stick together. They don't break apart. They like to be together, right? And so we're looking for ion combinations like that. And so when we look at HNO3, we have two ions there. We look at the H plus. Well, H plus, or hydronium, if we add water to that, this likes all bases. As we saw before. So this is number one. It's the same reactivity. And so this is overlap because it just so happens the cation is acid. We could have cations that aren't acid as well. But the nitrate, what types of things like to precipitate out with nitrate? Well, it turns out that nitrate is pretty unreactive in metathesis reactions. It's unreactive because nitrates, acetates, and chlorates are all soluble. Meaning that nitrate doesn't precipitate out with anything. And so no matter what partner you swap nitrate with, it doesn't bond together to form that precipitate. according to solubility rules. Does nitrate bond with anything to form a gas that bubbles out? No. No. Does nitrate bond with anything to form a weaker base? Well, nitrate is such a weak base, it's already neutral. And so basically for metathesis, nitrate doesn't do anything. But H plus does. And what we're looking at is we're looking at the reactivity of the ions. This is much easier than, these are all double replacement. And so we could do this. You know, we don't want to do this. This would be too tedious. So for example, if you wanted to figure out all the double replacement combinations, you do, okay, let's try nitric acid with lead chloride. Well, lead chloride's not soluble, so let's not do that. Let's try nitric acid with lead acetate. See what happens. Well, we're going to form acetic acid and lead 2 nitrate. Well, lead 2 nitrate's not going to precipitate. Acetic acid is good because we're going from a stronger acid, nitric acid, to weaker acid, acetic acid. So H plus and acetate like each other. Like I said before, H plus and acetate like to stick to each other. Whereas H plus and nitrate don't. And so, but we don't want to do every single A, B plus CD combination. There are too many. So what we want to do is we want to think in terms of ion combinations. In terms of ion combination, what ions does nitrate like? Well, pretty much nothing. You know? Does that make sense? We can get lead 2 or nitrate to precipitate out, but we have to evaporate all the water. We force them together. It's like sodium chloride. How can you get sodium and chloride to bond each other? Well, you got to evaporate all the water, and pretty soon it's like then they're forced together. Otherwise, they stay apart. All right, so this is the way we're going to start thinking about chemical properties. And let's try something here. Let's try this one as in class example. We're going to list the chemical properties of hydrochloric acid, HCl. So can you list the chemical properties of HCl? Okay, we'll try that. HCl is also a strong acid, you know, but there are some differences between HCl strong acid and HNO3 strong acid in terms of chemical behavior and chemical properties. So can you figure it out and look, you know, there's similarities and there are differences. So you can work with others on this and just try to figure out the properties here.